So in the previous examples, all the graphs we looked at were determined by the number of vertices. So there's only one Pn for a given n, and so on. Now we are going to look at not such specific examples of graphs, but more general types of graphs. An important type of graphs is what is called regular graphs. So a graph is regular if all the vertices have the same degree. If you want to be more specific, it's you can say that a graph is R-regular if each vertex has degree R. So let's look at a few examples. So the null graph is 0 regular. It is regular of degree 0 because all vertices have degree 0. Let's pause and think what you can say about Kn, Cn, and Pn. Are they regular? And in that case, what is the degree? Right, so let's start with Cn. So by definition, every vertex in Cn had degree 2. So Cn is 2 regular. What about Kn? What is the degree of each vertex in Kn? Well, each vertex in Kn attaches to all the other n-1 vertices. So each vertex has degree n-1. So Kn is n-1 regular. For example, K4, my favorite Kn, that's actually not true. I like K5 better, but never mind. K4 is 3 regular. What about Pn? Well, in general, let's look at maybe P4. So this is not regular because these two vertices have degree 2, while these two vertices have degree 1. So the only paths that are regular are somehow the tiny, almost trivial paths. P2 is 1 regular, and P1 is 0 regular. But these are very special cases. So in general, Pn is not a regular graph. Here's an example of a funny graph that will appear often. You know, all sciences have sort of a prototypical example that is somehow especially interesting or that is complicated enough to give you counterexamples. In graph theory, it's the Peterson graph. It's a pentagon with a pentagram inscribed in it in this fashion. And each vertex has degree 3. You can check. So it is 3 regular, and a short name for that is cubic. So cubic just is another word for 3 regular. So be familiar with the Peterson graph. It will appear time and again. If you have a theorem that says that every graph is such and such, and you're not sure if the theorem is true, test it on the Peterson graph. That gives you a good starting point. A cool example of graphs are bipartite graphs. So roughly speaking, a graph is bipartite if you can divide it into 2 sets so that the edges go between the 2 different sets and not within one set. So what does this mean more precisely? It means that the vertices of the graph can be divided into a set B, as in black, and a set W, as in white. You might argue that my white vertices look very red. That is obviously because I can't use white on white. And then you might think that times were better when we could use blackboards, but on blackboards you can't have black chalk, so there's always a problem with drawing such things. But anyway, the requirement is that no edge goes between 2 vertices of the same set or the same color. So maybe I can have something like this. This is one bipartite graph. So, as I said, another way to phrase this is that you can color the vertices black and white so that each edge has endpoints of different colors. And you can have many types of bipartite graphs. One such type are complete bipartite graphs. So what is a complete bipartite graph? It is a bipartite graph, but also it has as many edges as possible while being bipartite. So let's look at the same vertex structure as before, where we had 3 black and 2 white vertices. And now I draw all possible edges that don't violate this bipartite rule. So from every black vertex, there is one edge to every white vertex, like that. That is a complete bipartite graph. And such a graph is determined by the number of vertices of each color. So this is drawn K3. This is written K32 or K23, depending on which ones you count first. And this is the notation. And as I indicated, it doesn't matter if you count the black vertices first or the white vertices first, you get isomorphic graphs. So these are the complete bipartite graphs, KRS. Let's answer some questions. So how many vertices and how many edges do these graphs have? And what is the complement of a complete bipartite graph? I will leave these questions for you as exercises. You can try them at home, and we'll discuss them on Thursday if you want. And as always, if you are faced with such general questions about graphs, always look at an example that is small enough that you can draw it in little time, but big enough that it gives you an idea of the general phenomenon. So if you are not sure how to deal with this for general RS, try as an example to answer these questions for K32. You know, in mathematics, there is this general idea that if there's a problem you cannot solve, then there's an easier problem that you cannot solve. Solve that problem first. One particular example of graphs is that of cubes. So this might be a mouthful of a definition, but bear with me, you will see that it's reasonable. So what is a K-cube? A K-cube is a simple graph where the vertices are tuples of zeros and ones. K-tuples. So it's a sequence of a bunch of numbers that are all either 0 or 1. And what are the edges? Well, so it's a simple graph, so you only need to know whether or not there exists an edge between two vertices. And you look at the two tuples, and then you see how much of a difference is there between them, and you draw an edge if and only if the two tuples differ at exactly one place. Okay, this was a lot. Let's look at an example. This looks awfully familiar as a cube, and I claim that this is precisely the cube Q3. So imagine this is drawn in a coordinate system. So this point has coordinates 0, 0, 0. This point has coordinates 1, 0, 0. So it's a cube with side 1. And notice here that there is only difference in the first coordinate between these 2 points. That's why I draw an edge here. And if we continue, this is 0, 1, 0. To save time, I will not write the parentheses and the commas. Sorry, this is, well, it depends on how you label the axis. This is 0, 0, 1. This is 1, 0, 1. this is, which one is this? This one is 1, 1, 0. This is 1, 1, 1. And this is 0, 1, 1. Unless I'm mistaken, these are my vertices, and you can see that, for example, these two only differ in the middle component, and therefore there is an edge between them. The fact that the edges are dotted or straight lines doesn't matter. This is just for visualization. All are edges of the same kind. So how many vertices does the K-cube have? Well, this Q3, so it's supposed to be Q3, not O3, has, well, a cube has 8 vertices. 8 is 2 to the power 3. And in general, QK has 2 to the power K vertices. Why is that? It's because each vertex consists of such a sequence. So each sequence has K places, and each place can be 0 or 1. So for each place in the sequence, you ask 0 or 1, yes or no. So 2 choices, and you have K times these 2 choices, independent of each other. Now, the task for you that we will look at on Thursday is to show that the Q graph is bipartite. And a hint, you can pause if you don't want to hear the hint, but a hint is look at how many ones there are in each sequence. Can you divide the vertices into 2 groups depending on a certain property on the number of ones in the sequence, in the coordinate sequence of each point? And again, if it's difficult with QK, start with Q3.